Lecture 40, Fault Kinematic Indicators. There are several mesoscopic structures that can tell us the direction of fault movement. The first ones are mineral fibers. As shown in Figure A, fault surfaces are not smooth surfaces, but contain irregularities. Due to these irregularities, there are facets on which there is only shear, other facets on which there is contraction, and other on which there is dilation. As shown in Figures B and C, stylolites form on the contractional facets, and mineral fibers or slicken fibers form on the dilational facets. The slicken fibers grow parallel to the slip vector, and their steps indicate the sense of movement. The fault block moves down with the steps, not up and against the steps. The steps face towards the slip direction. Figure D shows a dilational facet on limestones, with slicken fibers of calcite. The steps indicate that the lower block moved to the right, while the upper block moved to the left, so this is a sinistral fault. This is a polished fault surface in grease. The polished surface itself is known as a Slickenside surface. On the Slickenside surface, there are striations, which are known as slicken lines. These slicken lines are parallel to the slip vector. The slip direction is difficult to tell. But congruous steps in the upper part of the surface indicate the hanging wall moved down. This is a normal fault. Gouging or plucking of rock material is also observed on fault surfaces. Figures A to D show different type of plucking structures on the fault surface and in profile view. Notice that the shape of the depression indicates the direction of fault movement. For example, in the picture which shows a concave depression in a fault surface, the hanging wall block moved downwards. This is a normal fault. Subsidiary fractures can be good indicators of the fault slip direction. This figure shows the fractures associated with a dextral shear zone. The reed arrow is the direction of maximum infinitesimal extension, which is at 45 degrees from the shear zone. M fractures are parallel to the shear zone, and P fractures are at low angle to the shear zone. Both M and P fractures have slip synthetic to the shear zone. In this case dextral slip. T fractures are tensional fractures, formed perpendicular to the maximum infinitesimal extension. Notice that there is no shear on T fractures. R and R prime fractures are called reedal fractures. R fractures are at low angle to the shear zone, and have slip synthetic to the shear zone. In this case, dextral slip. R prime fractures are at high angle to the shear zone, and have slip antithetic to the shear zone. In this case, sinistral slip. The orientation of all these fractures is better understood by superposing the infinitesimal strain ellipse. Figures A and B show the T fracture criteria. Figures C and D show the P fracture criteria. And figures F to H show the reedal fracture criteria. This is the top surface of a wet clay model under sinistral, left lateral shear. Figure A is the model before faulting. The big and small circles are initial markers. Figures B to F are incremental stages of deformation. The circles are deformed into ellipses, and low angle R and high angle R prime fractures develop. This is schematically illustrated in this figure. So, reedal shears are a great way to estimate the fault slip direction. Sigmoidal veins are also great fault kinematic indicators. In a shear zone, the infinitesimal maximum extension, which is shown by the red arrows, is at 45 degrees from the shear zone. Veins will first form perpendicular to the infinitesimal maximum extension, and at 45 degrees to the shear zone. With more shear, the old veins will rotate to higher angles, and new veins will form at 45 degrees to the shear zone. The result is an S-shaped or sigmoidal vein. The convex parts of the S point in the slip direction. Here is one example. What is the slip direction in this shear zone? Is the shear zone left lateral or right lateral? Here is the interpretation. The shear zone is left lateral. The convex parts of the S point in the slip direction. New veins form perpendicular to the infinitesimal extension, which is at 45 degrees from the shear zone. Notice the presence of breccia in some parts of the shear zone. The kinematic indicators we have mentioned so far are in the brittle regime. These are several types of shear sense indicators in the ductile regime, all for a right lateral shear zone. Figures A to F show flow of softer material around harder clasts, and rotation of these clasts. Figure G illustrates C surfaces, which are parallel to the shear zone, and S surfaces, which are parallel to the long axis of the strain ellipse. Figure H shows asymmetric folds, and Figure I shows inclined grains oriented along the extension. To learn more about this, read Chapter 10 of Fossen, and do his e-learning module on fault kinematics. And answer these questions.